I just want to thank all the organizers for inviting me here. This is a really, really fun topic because we'll all, or at least I will be talking about something I don't really know that much about because it's hard. So I appreciate the organizers for putting this together and inviting me, and I appreciate all of you for being here and trying to work on something hard, but mathematically, so to try and make it rigorous. And it's great to see lots of faces of folks that I haven't seen in a long time. So a little bit about me. So I work on quantum, I've always worked on quantum information and quantum technologies. I've been building quantum computers. Right now I run Unitary Fund's a nonprofit research institute that works on open source quantum tech stuff. And I'm a partner at a venture fund that invests in quantum technologies. But I'm not going to talk about that today. So today I'm going to talk about local friendliness violations and a bit about experimental metaphysics and the nature of the observer. So the type of consciousness talk this is one of these types. So we take one concept, observers, which is not very sharp, and another concept, consciousness, which is not very sharp, and we say, well, maybe these not very sharp things are similar in some ways. So you can keep this in the background. This may not be true, but keep this in the background. And the thread that is going to connect them in this talk is whether or not an observer or something that is conscious has an experience of an event. So whether or not we mark this object as having that experience of an event is important. To give you a quick outline, I'm going to start talking a little bit about what experimental metaphysics is and what the local friendliness assumptions are. Then I'm going to talk about how quantum mechanics, as usually taught, shows that we should violate these assumptions of local friendliness. I'll give an example with something called possibilistic local friendliness, which is a variant that's just a little easier to explain, and then talk about local friendliness violations in general. I'll comment a bit on the observer and an experimental program that comes from this theory in the second bullet. I'll talk about some definitions for observers and some open questions and next steps. And a lot of this really comes from some it's an old thought experiment that kicks this stuff off, like a lot of good quantum mechanics thought experiments from the 60s. But in the last few years, there's been some really sharpening theory work to make it more precise. And so I'll be summarizing a lot of the work of others and maybe packaging it into a bit of a perspective going forward. So what is experimental metaphysics? So the idea here is to use experiments to explore the space of different physical theories. And there are different versions of this that exist. So Bell's inequalities are one. These violations are one. So showing that physical theories to be consistent with the predictions of quantum mechanics and everything we've measured that matches the predictions of quantum mechanics can't be modeled with, well, one way to interpret them is you have to drop an assumption of local hidden variable theories. But there are other examples of these kinds of experimental metaphysical assumptions and violations. And I'm going to talk about one that's based on these two assumptions together. So a reference paper here is Bong et al. So we're going to assume there's a few ways of formulating these. I'm going to give one sort of a short one that's good for a talk. We're going to assume two things. We're going to assume something called the absoluteness of observed events. And we're going to assume local agency, the conjunction of which give this thing called local friendliness. And this is going to, if you make these assumptions, it's going to say something about how any possible physical theory should, what the predictions of any compatible physical theory should be if they're compatible with these two assumptions. It turns out quantum mechanics is not compatible with them. All right, so let's go in order of the two of them. So the first is absoluteness of observed events. So this assumption is that if an event happens, then it doesn't happen relative to any particular observer. So this is a stronger, well, in some way, well, I suppose a weaker condition compared to relativity. In relativity, we disagree about what time something happens. But here, we actually disagree about whether or not an event occurs. And this is really a physical event, like a proton decaying or something like that. So this should seem relatively natural to assume. The second thing to assume, and we'll do this more precisely in an example later, is local agency. And at a high level, this is an assumption that says that we can construct independent variables. So another way of saying that is an intervention can be made uncorrelated with some set of other events outside of its future light cone. But the fact that it's a future light cone and the fact that the nature of things being uncorrelated has to do with the speed of light is not fundamental to local agency. You just need to be able to say that you can have some variables that you know are not uncorrelated with others. You don't have to always be able to do this. You just have to be able to do it in particular settings in certain kinds of experiments. So this local agency, in summary, is that an event does not influence the probabilities of some other events. If you drop local agency, this is sometimes called superdeterminist ways of thinking about these experiments. It's sort of hard to do science because you can always say that some, well, and good, Tim's shaking his head, I like that. And so we'll talk more about that over the course of the workshop. All right, so Wigner's friend. The basic setup here is that there's Wigner, and he takes a friend, and he puts his friend in a box. And the box is totally sealed to Wigner. And you send in a, let's say, a photon or some quantum system that's in a superposition state, so in the plus state. So half 0, half 1. When the photon gets in the box, the friend then measures the photon. And from the friend's perspective, you get something that starts in a superposition of 0 and 1, and then this is the state of the friend at the beginning. The friend makes the measurement, and they either write down, oh, I saw a 0, and the system was in 0, or I write down a 1, and the system was in 1. So the friend is no longer in a superposition. But from Wigner's perspective, where nothing leaks out of the box, Wigner sees that this superposition, this product state, so the superposition of 0 and 1 and the friend state, shows that now there's a superposition between the system being 0 and the friend writing down 0 on one branch. And on the other branch, the system is 1 and the friend writes down 1. So the motivating kind of question here is that from the friend's perspective, there's no superposition. But from Wigner's perspective, there is a superposition. Who's right? And depending on whether or not you believe superpositions are real or they're things that are about information that observers have, this may or may not be uncomfortable. But this is the basic setup, which has been made more precise over the last couple years, even though this is 50 years old, 60 years old. So to make it more precise, we actually moved to something called extended Wigner's friend scenarios, which is sort of just two copies of the same we had before. We now have two copies of it because we found more people who are willing to be experimented on in boxes. So there's Alice, who has a friend Charlie. There's Bob, who has a friend Debbie. And for notation to set up all this stuff, there's a few choices that get made. So there's some initial system. It's a bipartite system, so we're going to create some state of that, send half of it to Charlie, and send half of it to Debbie. It doesn't actually have to be half and half. Send part of it to Charlie, send part of it to Debbie. Now, Alice and Bob are going to make they're going to have choices of what kind of measurements they make on this whole joint system. And those are defined by choices of x and y. So x and y are sort of measurement settings, which is what this cartoon indicates. The outcome that Debbie sees from measuring her system is some bit d. The outcome that Bob sees from measuring with choice y is some bit b. And likewise, with choice x, Alice measures bit a, and Charlie measures bit c. And it's worth emphasizing that a and b are just classical bit outcomes that are actually observed by observers. I'm going to slightly refine, just because it's an easier example to go through live, which is just to move from local agency to possibilistic local agency, which is a little bit weaker, actually. So previously, local agency said that an event can be made independent so that it does not influence the probabilities of other events in other regions of space-time. And in this case, we'll say, well, maybe the probabilities could fluctuate, but the possibility does not change, which means that something that has zero probability cannot become non-zero probability. So we'll just, this is the one that we'll do together here, and I'll refer you to the references to do more stuff on the regular local friendliness. And, oh, and this formulation is from this paper by Hadara and Cavalcanti. Good so far? Great. So it comes down, a little bit of this comes down to what do the choices of Alice and Bob's measurements mean? So with their settings X and Y, when they make measurements, what choices do they get to make? And so in this setup, I'm going to draw it as a quantum circuit, but I'll just kind of explain it as well. They're going to have two different choices they can make. So either Alice and Bob, they can either peak or they can reverse. What does that mean? So in the peak setting, the state is prepared. Part of it is sent. This is the state for Charlie, the state for Debbie. Part of the state is sent over to the box that contains Charlie. Charlie does a measurement, which to Alice looks like some kind of unitary observation, whatever this is. In the peak setting, Alice opens up the box and asks Charlie what measurement she got. Right? So Charlie's, as in the notation from before, Charlie's going to get some measurement bit C. Alice is going to look into it and set her A, which is her output, to C. So she gets the same thing that Charlie gets. So that's peaking. In the reverse setting, instead, so we have just proceeding like before. In this case, let's say Bob is choosing to reverse Debbie. Debbie's going to do some measurement, which should be modeled as some kind of unitary observation. But since it's unitary, Bob is going to reverse whatever that operation was. Just take the dagger, because quantum mechanically, every system can be reversed. Now, it might be very hard to do this. And instead, choose to measure in a different basis. So they're going to apply some, in this case, it's going to be a Hadamard. So Bob is going to apply some operation to the system and measure in a different basis. So these are the two different choices that Alice and Bob can make. Questions on this before I go on? Yeah.
So basically just mean like diagonal or computational or something like that?
Yeah, so more generally, you can have different choices, different bases, but for this possibilistic version, it's just going to be, yeah, we're going to do a Hadamard, so either an X or Z. Yeah. Cool. All right. So why does this cause anything interesting? So the setup again, right, we have X and Y are the different settings of measurements that people can pick, and there are measurement outcomes that Alice and Bob get. So we're going to call an event, some event that occurs for a setup like this, a quadruple of bit A, bit B, measurement X, and measurement choice X and measurement choice Y, which are Alice and Bob's. So imagine that the following set of events could be made possible and impossible. Let's consider that. So consider that event 1, which is where there's both Alice and Bob get bit 1, and they both choose to reverse. When they both choose to reverse, imagine that that's possible, like that can occur. However, at the same time, each of these three is impossible. So this is Alice gets a 0, Bob gets a 1 when Alice peaks and Bob reverses. Or when they both choose to peak, they can't both get a 1. So let's just consider that that's possible. And then let's reason about what that might mean given our assumptions of local friendliness. All right. So absoluteness of observed events. So that means if we assume absoluteness of observed events, then that means that the measurements that Charlie and Debbie make are real. So that means that we can extend our event of 4 to an event of 6, where there are some choices of what measurements Charlie and Debbie get. So event 1 from before is 1-1 reverse-reverse. So in that setup, where we have 1-1 reverse-reverse, there are some real outcomes for Charlie and Debbie. And we haven't said what they are. They're just 0 or 1. They're just a bit. That's all we said. So that's by absoluteness of observed events. And importantly, these are not hypothetical events that might have occurred. They're observed events. Charlie and Debbie are real observers. People observe, well, observers observe them. Right. Secondly, by possibilistic local agency, Alice can choose, but when Alice changes her measurement choice, it can't affect B or C or D, because it happens after those observations have occurred, and you can separate them in space-time if you have a great lab. So that means we can, what it will affect is what Alice gets. So in this setup, we had reverse-reverse. So we're going to say Alice is going to unilaterally decide, OK, instead of doing that, I'm going to peak. That should leave all of these variables the same, but potentially change her outcome. And we can do the same thing for Bob. So again, we start here. Instead of reversing, Bob will peak. All the rest will stay the same, except Bob's, which might change. Or we could do it for both. In that case, they both peak, in which case both their outcomes are the same, but it shouldn't affect what happened to Charlie and Debbie. OK. So this is just copying what I showed you on the previous slide and writing it down over here, calling them E5, E7, E6. But the definition of peak says that if, so let's take the top one here. So if Alice chooses to peak, like in this setup, then Alice should get the same result as Charlie. So A is not free. A actually has to be the same as C. So that's how we get the top one here. The second one is the same thing, but for Bob. So Bob has peaked, so B needs to be the same as D. And the third one, they both peak, so A prime and B prime need to be C and D. But this leads to a problem, because if we take E2 and E5 together, so both of those are peak and reverse, this should be impossible, whereas E5 is possible. So that means that C it's impossible for it to be 0, so C has to be 1. Then we take E3 and E6 together, and by the same argument, we look at the second index. It's a free D. 0 is impossible, but D, so D has to be 1. Then we look at E7 and E4, and we see it's peak-peak, CD. This says that it's impossible for them to both be 1.
Sorry,
Yeah.
Sorry to interrupt. I think this is more or less exactly the Bell theorem without inequality, right? From Greenberger, Shimon.
It's not quite that one. So it's more like something like Hardy paradox setup. This one is a little bit.
They also have multi-particle entanglement. They
Yeah.
also show if you have independent choices, you get this contradiction. So where is this different then?
So the difference here is that what you've used to do the reasoning is that you have used this absoluteness of observed events setup. So there are ways to build, there's different paradoxes and different kinds of all versus nothing paradoxes you can build up arguments like this from, if you know those, people who know those ones. The difference here is you're adding observers into the systems and saying that a key fact that you use to reason is that certain events for them are real. But you can construct different, this is similar to other like GSF paradoxes and things. So it's not, in some ways it's like not that complicated of an argument. But so this all began with me saying, consider that you have one event that's possible and a bunch of them that are impossible. And is that true? And you can make it true. And if you choose that the system is this system, and you work through just textbook quantum mechanics, then you get the possibility and impossibility that I began this chain of reasoning with. Which, at least for me, it should make you uncomfortable if you haven't seen it for the first time. It made me uncomfortable. So how does this relate to Bell? So that was the possibilistic version. I'm now going to move to the non-possibilistic version, just to show the polytope. So basically, it's weaker than Bell inequalities. So here we're plotting Bell in the green, local friendliness in the orange. So there are some local friendliness conditions that are weaker than Bell conditions. No signaling is in purple, and quantum in the red. So where you can construct quantum violations. So basically, this is saying that quantum systems can violate Bell inequalities. They can also violate local friendliness inequalities, but we're still inside of the no signaling polytope. And this has been, you can do an experiment. It's kind of simple. The question is, how do you interpret the experiment? So this experiment was done a couple years ago in a photonic setting. And so in this setting, the Charlie and Debbie, the friends, were themselves each a single photonic qubit. And there's actually you can break down the different inequalities that come into different categories. And the violation is when it's above 0 in this setup. And what they do here is they tune, you can think of this mu on the x-axis as they tune the fidelity of the quantum operations that are being used. And so as the quantum system gets more pure, you start to see the violations. So what should we think about all this? What are the implications from those violations? I think there's 3 things you could do, potentially more, but at least 3. One is drop absoluteness of observed events, which seems pretty radical, at least something to have experimental evidence to drop. 2 is to drop local agency, which I find hard to drop, but would love to talk with more people about. And the third, which is maybe easiest, is to just deny that a photon is an observer. And to say that, you did this little experiment and a photon measured something, but like that photon didn't have an observed event. So that third one might seem the easiest, but it's also interesting, at least some other further interesting questions. For example, what does count as an observer? If a photon doesn't count as an observer, then what does? And here the question, the sort of most meaty point that matters is it needs to be something that has a reality, something where when I do this absoluteness of observed events argument, it applies, that I believe that the reality that it has, if it's different than mine, would make me concerned that reality isn't objective, is not an objective thing. So you could imagine from this initial experiment a program of local friendliness violations where you start with this one photon violation that's already happened. And at the other end, you do it with a human friend. Because while we don't, or at least I don't know of a well-accepted definition of an observer, we seem to agree that people are. And so there's something in between a photon and a friend that becomes more and more observer-like. So let's say you did this. I have no idea how to do this experiment with a friend, but let's just think it through. So what are the options of what could occur? Well, one thing that could occur is you I'm just going to use the observer-like is not defined here, but let's just move with it for a bit. Let's take systems that are more and more observer-like, and each time we get a local friendliness violation. So while we're doing that, we're accumulating more evidence that one way to say it is that you're accumulating more evidence that local friendliness is violated by reality. And then eventually, our great-grandchildren or something do this with a person, and we really believe that local friendliness is violated. So one way things could go. Another option is that we see violations for a while, and then they stop. And you could interpret that by saying that everything below this was not an observer, and everything above it, I mean, maybe it should be monotonic, but everything above it is an observer. And it might not be sharp, but that would be one also thing that could happen. And this would be useful because it would give us a definition for observer. And this is option 3, which is just something weird. There are folks who think that there are modifications to quantum mechanics that cause some kind of collapse, where once we start to work in a different regime, which maybe observer-like starts to move us into that regime, we start to see behavior that's different than we expect. I have no idea which of these options is going to happen, but I think they're all important to consider. So what could be observer-like dimensions? We ran a few workshops on this recently, actually, that a few people were at. So some ideas, there could be more ideas, more mass, more complexity, more degrees of freedom, more agency, more consciousness. So for example, more mass is definitely one interesting one. And one way you can think about that being an issue is in order for Alice or Bob to unitarily reverse, to do the reverse choice on the friend in the box, they can't lose they can't get any information about what the friend's measurement was. That has to be shielded. But it's hard to do with mass. So imagine, I'm in the box and a photon comes in, and when I measure 1, I move over here. And if I'm here and I measure 0, I move over here. It's very subtle, but outside the box, you're going to detect the gravitational shift from my mass moving based on the measurement outcome. And this is an issue because unlike electromagnetic radiation, gravity, we don't know, or at least I don't know how to shield it. So maybe once you get to something with some level of mass, we're unable to keep performing this experiment because the information leaks. So that's the mass one. The conscious one. Well, one thing to think about with the conscious ones is there's kind of one interesting proposal. Again, it's from Howard Wiseman and Eric Convocanti and Eleanor Riefel, is, well, let's think about what's at this end of the spectrum. So we can't do a human friend, but maybe something easier than a human friend, but still very science fiction, is to run a simulation of an artificial general intelligence, but a simulation of an AGI that's running on a fault-tolerant quantum computer. And if it's running on a quantum computer, then we can reverse it unitarily. It's a unitary operation. And they actually did an estimate of sort of just based on brain size and kind of estimates of how big of a quantum computer you would need in order to do this. It's big. But at the least, it's an interesting thought experiment to ask, what are the properties of this that would make us say that this is an observer when a photon is not? That's also worth thinking about. Another thing to think about, there's this, someone mentioned this actually in the Slido as maybe a discussion topic. There's a summary article about consciousness in AI. You could pick, these are some different properties, relatively, some qualitative, quantitative. You could take, the question is, what is your friend system going to be? What are the properties of that friend system going to be? And so you could pick the friend to have some of these properties. But I'm going to propose a different one. I mean, there's a bunch of different directions you could go for observerness. But there's a very recent paper kind of coming out of some workshop discussions we had a couple months ago, where it's a new notion, a new metric called branch factor, or maybe we're calling it branchiness. It's one of those things where we haven't really settled. Maybe we'll take a vote. And the idea here is that a branch, so this is an observer really making a 0 versus a 1 measurement. It occurs when, depending on, I guess, whatever, we'll just go with the quantum terms. It occurs when you can't model the difference between a classical probability distribution and the quantum distribution. It occurs when those things are the same. So I'll just take you through kind of this definition you can skip this part if you don't know the quantum. We can talk about it more over lunch or something. So one initial term we need is the relative state complexity, which is just the minimum number of local operations in any quantum circuit that create this state with some up to some fidelity, some error budget delta. And then we need two more terms, something called the distinguishability complexity. So that is given two states, how many gates, sort of like how hard is it to tell the difference between these two quantum states. That's how you should think about it intuitively. Then there's another metric, which is the interference complexity proxy, which is given two states. How hard is it to get them to interfere? So to recombine them in a way that wouldn't be modeled by a classical probability distribution. So these two metrics broadly correspond to how easy is it just classically to tell the difference between two states, and how easy is it to see if modeling them classically is wrong, to do something with them that wouldn't be classical. And the way to think about this is those two states are the states of your friend when they make the measurement. Okay, so what's the metric? So a good branch decomposition is when your interference complexity is much bigger than your distinguishability complexity. So again, kind of like in words, if you're trying to build a detector, so the question here is sort of, when you walk into a laboratory and nobody tells you what the labels for things are and you just see them as physical systems, how do you know which ones are the detectors and which ones are the system? And one way to tell is to look at arguably, is to look at these quantum states and to say a detector has states, or an observer has states, where the distinguishability complexity is low. So it's easy to tell the difference between the two outcomes, red light on, green light off. These, I can see them, they're big. But it's hard to recombine them in a way that isn't well modeled by a classical probability distribution, to get them to interfere as if they were still in some kind of quantum state. So you can turn this not just into a condition for being a good branching, but to being a definition of branchiness, where you just look at this value. So what I like about this metric is you can start applying it to things and using it as a larger and larger observer-like system where you get increasingly better and better branches in the systems that you choose to be your friends. So a couple examples for sort of common quantum states. So let's say you don't want your friend to be a single photon, but you want your friend to be an n-qubit system. And what the friend is going to do when they make a measurement is they're going to turn into it's going to be a GHZ state. So here, the interference complexity is of order n. The distinguishability complexity proxy is of order 1. So that's pretty good. So here, the two states you get are either the 0 state or the 1 state in this superposition as the observer. Another example is you could start in the 0. You can have your friend start in the 0 state, and then based on what measurement, if the photon is 0, they stay in the 0 state. If the photon is 1, then your friend goes into a random quantum state. So there's like a hard random unitary transformation that happens to your friend, and this is actually better. So here the interference complexity is higher, it's exponential in n. And then if instead of having 0 photon be 0 friend, 1 photon be random state, you have 0 photon be random state constructed with a random quantum circuit of depth d, and 1 of the photon cause the friend to go to a state with a random quantum circuit of depth d2, then you get these corresponding interference and distinguishability complexities. So why am I talking about circuits as the way to construct measurement states for observers? Well, those are the things we can run on quantum computers. So you can start putting a quantum computer in as a friend and choosing to construct different states based on the way that quantum computer friend system interacts with the system. And you can choose what protocol you use so that you get a good branch factor, or at least one of like an increasing amount of branchiness. So just to like be really, really reductive, like if we just choose G8Z states, my quantum computer can have the photon come in. I do a C0 gate with n equals 1, and that will give me some level of branch factor. That's kind of what happened in the original experiment. If instead I have an n-qubit register as my friend and I just do a C0 ladder, I'm going to get a higher branch factor. And so you can start to proceed this way. I mean, I think there's a lot more in this paper about the relationship between good branching factors being kind of the opposite of error correcting codes. And maybe in the interest of time, I'll just refer to it. So to sum up a little bit, I don't know the answer to any of these. So can good branching say something about emergent consciousness? One reason you might think it does is that if you want to believe in absoluteness of observed events and you want to believe in local agency, then at some point there needs to be some kind of good branching that determines when the event that happens for a system actually matters. And you might want to say that that's related to consciousness. Secondly, and maybe more quantitative, can we calculate the branchiness for particular systems that we believe should be good branchers, like a photodetector or potentially a brain? Is there a relationship between good branchings and different choices or some kind of agency that occurs? I do not know. But one thing that I'd definitely be curious to talk about more and that I'm working on with collaborators is to try and violate local friendliness with friends that are better and better branchers. And you can either think about doing this with quantum computers or just with quantum systems that you can design and control, but that have these properties of being good branchers. All right. That's it for me. Thanks, Ian. A little early.